Last time we stopped, well, I introduced the space of Hermitian matrices n by n. Up. And the coefficient Zij, I said I would consider as coordinates on this space. Then I introduced a quadratic form, a positive definite quadratic form. The trace of the product of two matrices. And I showed that the expectation value of Zij, Zji for this quadratic form was equal to 1. And the expectation value of any other product of two coordinates was equal to 0. So today I'm going to compute the following. I think I'll write it down. First of all, I will multiply my quadratic form by large n, by the size of the matrix, and I will compute the expectation value, so maybe I'll just write it down. 1 over k trace of x to the power k. I guess I'll even write it like that. N over k, that's the best way to put it. And I recall the definition. So it's a quotient of two integrals. The first is n over k trace x to the power k e to the power minus 1/2 n trace x squared dn squared x divided by the integral of e to the power minus 1/2 n trace x squared dn squared x.
Oh, I forgot.
Yes.
The matrices are Hermitian.
The matrices are Hermitian, yes. So that's exactly the definition of an expectation value that I gave you last time, with this being the quadratic form. And since my quadratic form is now n times trace of xy, it's easier for me because I can correct it on the blackboard. So for this quadratic form n times xy, its inverse matrix is n times smaller than the inverse matrix of trace xy, so the answer is modified in the following way, like that. The expectation value is divided by n. Did it work? Okay, I think here. Okay. So let us compute this expectation value. To do that, I will draw the following picture. Okay, this is a crossing in the city with K streets. The same K as the k there of x to the power k. So this picture is going to symbolize the well, this is to symbolize 1 over k trace of x to the power k. Why is this? Because I will write in detail what trace of x to the power k is. So this is 1 over k, sum over I1 ik of zi1 I2 zi2 I3 etc. zik I1. When I multiply k matrices, I get a product like that, and then when I take the trace, I impose that the first index should be the same as the last one. So here on this picture, I will just put the indices I1, I2, I2, I3, I3, I4, and so on until ik I1. So now, first of all, the index is preserved on each line, like that. This is the same line, so the index is I2 both times. And every street represents one of my ZIs, ZIJs, well, I1, I2. And I should sum over all possible ways to attribute the indices. Sum over all I1, Ik. So that's the first step. This is just the way to write out to write out this trace of x to the power k. Now I will apply the weak formula. I guess I should write it down again, because it would be too much to expect of you to remember it from the first time. So that's the sum over pairings product over pairs LA LB. So now we should sum over all possible pairings of streets. And I will draw a pairing of streets in this way, for example. Well, this is one pair. And maybe I can draw another pair like that, and another pair like that, and yet another pair like that. So this is a pairing now. In the end, I should sum over all possible pairings. Finally, what is the contribution of this pairing to this formula? Well, I should look at every pair and see what its contribution is. So let us look, for example, at the first pair that I have drawn. So this will be I5. No, this is I4, I5, I5, I6. So what is the contribution of this pairing, of this pair? Here I have the expectation value of Z, I2, I3, Z, I4, I5. In most cases it is equal to 0. And if it is equal to 0, then this product immediately vanishes. I think I should erase something. Yeah. Let me write it here. Zi3, I4. No. Zi2, I3. Zi4, I5 is equal either to 0 in most cases or to 1 over n if I2 is equal to I5 and I3 is equal to I4. Right, so in the end, what do I get? Yeah.
Am I right if I think that you are trying to use weak formula
Yes.
to multiply of z in E1, and so on, E1, E2, and so on and so forth? Yes. As LA and B.
Yes, yes. Here LA, yes, exactly. So here L1, L2K are these linear forms. This is L1. This is LK. So here actually I numbered them from 1 to K, but K should be even, otherwise it won't work. Well, otherwise the answer will be 0.
Thank you.
So rule. Okay. Draw all pairings of streets. Put an index from 1 to large N to capital N on every closed line. This will give you 1 over N to the power K over 2. And then you sum over all possible ways to do that.
I didn't understand the next to last thing you said. So you put the indices, and then what you've written is arrow 1 over large N K over 2.
I'll show you. So let me do it again. I understand that it is not clear yet. Yeah. So these are my streets. I draw just one random pairing. I think it's the same one, right? As before. Then I put some index I here. So since it's the index I here, it should be the same index I here, because that was the rule for computing the trace. Now if it's the index I here, it should also be the index I here, because otherwise this pair will give a 0 contribution and all the products will vanish. Now since it's the index I here, it is also I here. And also I here, and here, and here, and here, and here, and here. Yeah, and that's all. So this is actually one index I associated with the closed line. Maybe I'll draw it in a different color. Let me draw it in blue. Yeah. Okay, so all this is one closed line. And along this line, the index I has to be the same all the time. It's the same in each angle like that, because that was the rule for computing the trace. And it is also necessarily the same on two sides of one street, because otherwise we won't get the expectation. Well, we will get a zero expectation value if we don't have streets with Zij on one side and Zji on the other side. We get a zero contribution of the corresponding streets. And then there is another closed loop, and here we can get another index j. Not necessarily the same, but that could be the same. So now assume that we have already chosen this pairing, this particular pairing, and this particular way to put the indices. Now let us evaluate the contribution to the weak formula. So here we have three edges, and each edge contributes 1 over n to the product. So this picture will give a contribution 1 over n to the power 3. And in general it is 1 over n to the power k over 2.
So it's for example, for these, for the i's and j's that you have on the...
Yes. So in this picture, let us take k equals 6. The expectation value of n over k trace x to the power 6 is equal to the sum over pairings of streets. Well, first of all, I think I should put n over 6 here. Sum over pairings, n to the power number of loops, times 1 over n to the power 3. Right? So it will be 1 over 6 n to the power 1 minus 3 plus the number of loops. Yeah, that's right. Or I can write it again as 1 over 6 n to the power number of crossings. Yeah, I don't have the place to write it here. Let me write the answer in the general form. The expectation value of 1 over k, n over k, trace x to the power k equals the sum over pairings (1 over k) n to the power 1 minus the number of edges, well, the number of streets, plus the number of loops. Okay, so now maybe I should explain well, I should explain two things. I don't know which order is best. So 1 over k is a way to take into account the symmetries of the picture. Because actually it is nicer if I count as the same picture, the pictures that I obtained one from the other by rotation. And the second thing is well, the second thing is actually a construction. So let us look at this picture. Construction. Look at this picture and glue a disk into each closed loop. It's a very simple construction. It holds in just one sentence. Glue a disk into each closed loop. What will we obtain? First of all, I say that we will obtain a closed surface without boundary. Here, if you look at this picture, this is already a surface, but a surface with boundary. You see, it's a very thin surface, but this is clearly a surface. The surface of all these ribbons. By the way, this picture is sometimes called a ribbon graph or a fat graph. So this is already a surface, but it has a boundary. My blue line and the white line constitute the boundary. But now I take two disks. Well, the boundary is, here in this example, the boundary is composed of two circles. But now I take two disks, a white disk and a blue disk. And I glue them to the surface along the boundary. So the white disk will be glued here, this is easy to see. And the blue disk will be glued to everything else. This is maybe more difficult to imagine, but I can help you by drawing the final result. So the final result will actually be a torus, a surface with one hole. Here is the point out of which the 6 streets issue, and we will get something like that. So there is one simple loop like that. This is the white disk, and then we get, let me see.
In other cases, we'll get surfaces of different genera.
Yes. Okay, so this is the white disk, and everything else, all this area on both sides of the torus, is the blue disk. If you have good spatial imagination, you can readily see that if you cut the torus along the white lines, what you obtain is indeed a small white disk and a big blue disk. Okay, so now I say that there is a way to compute the genus of the surface by just looking at this picture. There is the Euler formula for every graph that cuts Sorry, I should take more space to do things. It will be much better. So for every graph that cuts a surface with G handles into disks, we have 2 minus 2G equal to the number of vertices of the graph minus the number of edges of the graph and plus the number of disks. So please, could those who know this formula raise their hands? Okay, that's good. There were some you don't know, right? Did you raise your hand? Yeah, okay. So, well, that's that's good. That's very good news because it means I can use it. Use it easily. So just by looking at this picture, I can immediately compute the genus. So here I say that the genus of the surface, well, 2 minus 2G, is equal to 1 because there is just one vertex here, minus the number of edges, the number of streets, and plus the number of loops, because I glued a disk into every loop. And this is precisely what appears here. Of course, it is not a coincidence. I arranged everything to obtain this result. So finally, this is the sum of graphs with one vertex. It's longer to write the what we're summing over than to write the sum itself. Graphs with one vertex of valency k embedded into a surface. And the sum is just n to the power 2 minus 2G times 1 divided by the number of symmetries of the graph. Let me call the graph G, and then
the embedded graph.
Embedded graphs, yes. Embedded into a surface, yeah.
I'm sorry, maybe I should ask this question, but what do physicists say about the surface? Does it have a physical meaning? Or is it just a tool used for computations?
Well, it depends on the physical problem you are looking at. Here here there was no physical problem. I just computed an expectation value of the trace of x to the power k. So it does not have any any physical meaning. But this kind of integrals indeed do appear in real physical problems, and the corresponding graphs are called Feynman diagrams. So, yes. So, well, the difference with the true physical problems is that they have infinite dimensional spaces. So they not only have to sum over all possible graphs, but they have to sum over all possible positions of the vertices of the graph in space. And then they interpret them as all possible interactions between particles. So every vertex of the graph is an interaction between particles, and then the edges are the trajectories of the particles between the interactions. So if you look at papers of nuclear physics, you can see some, I don't know, 2 gamma photons interacting to give an electron and a positron, and then they go somewhere and annihilate again, for example. So you have a graph there like that. They have some special notation for trajectories of different kinds of particles. So this is one of possible graphs, except that you have also to sum over all possible places where these interactions take place. So it does not help so much because the corresponding sums do not converge. Here we have completely solved the problem because we obtained a finite sum over a finite set of graphs.
What is the summing of over the smalls assumed? Or
Sorry?
what about genus?
Yes, arbitrary genus. Yes, so all.
So we sum over.
Yes.
So should.
Surface of any genus G. Yeah.
Or we include there.
Maybe I can give an example of. Yeah. Let's look at the cases k equals 2 and k equals 4. So for k equals 2 there is just one graph, like that. And it is embedded into a sphere. Maybe I'll draw it as a ribbon graph. And it is embedded into a sphere, so you can see 2 closed loops. And when you glue disks to both loops you obtain a sphere. And this graph has symmetries of order 2, right? Because you can turn it by 180 degrees. So this will give you the contribution of 1/2 n squared. And for k equal 4 you have 2 kinds of graphs. One graph like that. Genus 0. And symmetry order 2. And one graph like that. This one is genus 1, and the symmetry group is of order 4. It is not so obvious the way it is shown on this figure, but actually I can draw this loop downstairs or upstairs as I wish, or just as a straight line. So if you turn this graph by 90 degrees, you will obtain the same graph. So the answer in this case is 1/2 n squared plus 1/4. Are there any questions? I'm going to show you a generalization. And this will be the end of matrix integrals. So do you understand this? Okay. So the generalization is to graphs with more vertices than one. It was obviously a limitation of this computation that it only concerns graphs with one vertex. Now what if I would like to enumerate graphs with more vertices? So as an example, let us consider graphs with, well, again, embedded graphs.
These graphs were not embedded.
No, they are embedded.
Space.
No, in surfaces. They are embedded into surfaces. Yeah.
Okay.
Embedded graph with any number of degree, well, of vertices of valency 4. And this is just an arbitrary number. I could have very well taken any other. It's just for historical reasons. These were the first to be computed, so I decided there was no reason to change. Yeah.
А это соответствует, скажем, случаю, когда мы будем вычислять след там произведения нескольких матриц?
Да, вот сейчас я покажу, да, сейчас я напишу интеграл, который ровно это вычисляет. Okay, so we should compute the expectation value of the following. 1, this is the case of 0 vertices. Now if we have one vertex of degree 4, we already know what we have to do. This is n over 4 trace of x to the power 4. Now if we have two vertices, I say that we should do the following. We should write 1 over 2 factorial n to the power 4 trace of x to the power 4 squared, and so on. So this is the contribution of graphs with 3 vertices, and so on. Yeah. And in short, this is the expectation value of e to the power n trace of x4 over 4. And maybe it is even better, I will add a variable lambda that will count the number of vertices. And then I just add a lambda here. Okay, so let me explain. Let us consider, for example, the contribution of this term. As before, I represent every trace of x to the power 4 with a picture like that. But now I have 3 traces of x to the power 4, so I draw 3 pictures like that. Okay, now I have to choose a pairing between, well, every half street here represents a variable zij. Now I have to choose a pairing between these variables. So I can choose a pairing, no, something like that. This is an example of a pairing that I can choose. And now I go the same way as before. I have to put an index over each closed loop. So I put an index I here, then it's the same index I here. Then if I want to get a non-zero contribution, it has to be the same here, and that's all. And here I have J and K. Yeah.
Is it possible to, можно вот коробку убрать?
Коробку
На столе стоит.
можно. Yeah. And this graph, as before, will give me a contribution, so every edge will count for 1 over n, because as before, the expectation value of Zij, Zji is equal to 1 over n. So this graph will contribute 1 to the power n, 1 over n to the power number of edges.
So this is the component to the right, yeah?
No, that's all the graph. That's the, yeah. And unfortunately, well, that was the purpose of this example. Unfortunately, the graph is not necessarily connected, because there is nothing that tells us when we choose the pairing. Well, in the weak formula, we can choose really an arbitrary pairing. So there is no reason for it to be connected. So unfortunately, it is possible to obtain this graph, and then I can proceed as before and glue a disk into each closed loop. Well, and then I obtain a graph embedded into a surface, but it is not a connected surface. So in this case, I will obtain a graph embedded into a surface that is a union of a torus and a sphere, with a graph like that in the sphere, and a graph like that in the torus. Yeah, that is a little bit unfortunate, but I will show you how to correct this. But at present, this is the answer we obtain.
Скажи, пожалуйста, откуда вообще взялась вот эта формула с экспонентой?
Формула с экспонентой взялась из суммирования этих членов.
Откуда взялись суммирование этих
Yeah.
членов?
Yeah, okay, so now that's what I'm explaining now. I am explaining that this term, for example, computes correctly the contribution of graphs with 3 vertices of valency 4. So I wrote out the sum, but now I consider just one term to give an example. So let us see what I'm trying to compute the expectation value of this term. And then I proceed by using the weak formula. So this term can be represented by a union of 3 vertices, because there are 3 traces of x to the power 4. Okay, trace of x to the power 4 is, let me write it somewhere. Trace of x to the power 4 is equal to sum of Zij, Zjk, Zkl, Zli over all possible I, j, k, and l. So it is natural to represent it in this way, by putting the index I here, j here, k here, and l here. And then this will be Zij, this will be Zjk, and so on. And then I make the pairing between my Zijs and Zjks by completing the streets, joining the half streets to each other. And then I compute the contribution of this graph. And the contribution of this graph, well, if I choose an index assigned to each loop, then the contribution is this. Or maybe I can write n to the power number of loops. Because if I have, when I have the graph, I have to choose an index assigned to every loop. And there are n to the power number of loops, ways to choose an index in each loop. So here, for example, I have to choose I, j, and k because there are 3 loops in this graph. Loop 1, loop 2, and loop 3. Okay, so finally we obtain that the expectation value of, maybe I should explain one more thing. So y I divided by 4 and y I divided by 3 factorial. I divided by 4 for the same reason as before, because I want to consider as the same the graphs that I obtain from each other by rotating the vertex around itself. And I divided by 3 factorial because I do not want to number the vertices. If I just take trace to the power 3, it would correspond to graphs with numbered vertices. And if I want to forget the numberings of the vertices, I should divide by 3 factorial. So
say draw your second connected component on the left of the right one?
Yes, this is just,
If you flip them, it's the same graph, right?
Yes, it's the same graph, yes. So the expectation value of e to the power lambda n trace x4 over 4. And maybe I even will write out again what this expectation value is, because it's a nice thing to write. So it's integral of e to the power minus n trace x squared over 2 minus lambda x4 over 4. And here just the integral of e to the power minus n trace x2 over 2. Okay, so I just wrote the complete formula to show that here I can regroup the measure I'm using, the Gaussian measure I'm using, and the function that I'm computing the expectation value of. And so this is the sum over embedded graphs not necessarily connected. Graphs with vertices of valency 4. And every graph contributes n to the power 2 minus 2g, n to the power the Euler characteristic of the surface. Since the surface is not necessarily connected, it would be wrong to write 2 minus 2g. The surface is composed of several connected components, so the Euler characteristic is just the sum of Euler characteristics of every component. Then I have lambda to the power number of vertices and divided by the number of symmetries of the graph. So that's the answer for this, well, the result for this expectation value, and I think you understand that if instead of putting x to the power 4 divided by 4, I write x to the power 10 divided by 10, I will obtain the sum over graphs with vertices of degree of valency 10. And okay, problem. Problem for you to do. I call this z of lambda, and I call f of lambda the logarithm. Oh. So problem, prove that f of lambda is exactly the same sum, but a sum over the connected graphs. And now I can write n to the power 2 minus 2g, lambda to the power number of vertices, and divided by the number of symmetries of the graph. This is a general principle in combinatorics that by taking the logarithm you go from disconnected objects to connected objects, and by taking the exponential you go from connected objects to disconnected objects. But I don't want to explain it now because I have one more subject to cover. Okay. So now I want to give you an example of a not well-defined problem. Because actually, if you are a physicist, you most often deal with ill-defined problems. So this is a problem called, it has a very beautiful and fancy name. Quantum Riemann two-dimensional gravity. So the problem is the following. You take a surface, let's say it's the following way. Okay. So I have to describe a system in statistical physics. So first I describe the states. A state is a surface. A state is a surface, not necessarily connected surface, with a metric.
The set of states.
Yes, this is the set of states. Okay. Well, this is supposed to be, well, a Riemannian metric, for example. It's not, okay, it's not so important. And then the energy of a state is given by lambda times the area of the surface. So if you have a surface with a metric, you can compute its area, plus kappa times the integral of the curvature. of the metric. And here we are lucky enough because for surfaces the integral of the curvature, there is the Gauss-Bonnet formula that kappa and lambda are two constants. So kappa and lambda are two constants. Lambda is called the cosmological constants. And kappa is called the gravitational constants.
А у нас состояние это многообразие вместе с метрикой, одно многообразие это одно состояние?
Да. Yeah, two states are different if the surfaces are not isometric. So maybe I should write here somewhere up to isometry. Okay, so here there are two constants. One of them is trying to make the area as small as possible. And the other one is trying to make the surface as flat as possible. So if the surface
will be made precise sense when you introduce the action, yes, that you still did not.
I won't introduce any action. I'm in statistical physics, so there is
You
this.
just want the
Yes.
energy to be the smallest possible.
No, well, now I want to compute the integral. The problem is to compute the integral of e to the power minus lambda times the area plus kappa times 2 minus 2g. The integral over all possible surfaces with a metric. Well, in general relativity, you have a four-dimensional manifold with a Lorentzian metric, and this is and you have a similar formula for the action, except that it is even worse because it's four-dimensional and the metric is, it's more difficult to deal with Lorentzian metrics than with Riemannian metrics. So here we do two simplifications. The first is to go to a two-dimensional manifold instead of a four-dimensional manifold. And the second is to consider Riemann metrics instead of Lorentzian metrics. And it is called two-dimensional, that's why it is called Riemann two-dimensional gravity. So it's actually a toy model. And the advantage is that we can do something interesting.
And quantum is because of the different types of surface?
Quantum is because, quantum is because I'm summing over all possible states. In classical mechanics I would just try to find the minimum of the minimum of the energy, for example. I would just,
What's the role of the partition function in this?
That's the partition function.
So we're actually asking to do
Yes. Of lambda and kappa. Sorry?
Are the surfaces connected or
No, not necessarily.
what is it? 2 minus 2g probably.
Yeah, okay, yeah, right, sorry, I should. Yes, the Euler characteristic. Okay, so in principle, if you have a problem in classical mechanics, then you are looking for the minimal, for the, extremal points of the action. And in quantum mechanics, you take the integral of the action, e to the power I times s over all possible states. So here is, as I explained, it is a it is a parallel between the problems in statistical physics and problems in quantum mechanics. Here I also perform an integration over all possible states. Then I can try to put an I here and I will obtain a problem in quantum mechanics. Okay, so I have really very little time to. So this is a nil-defined problem because this integral cannot be computed. And I'm going to present, well, there are 3 different models. I think I'll try to do one of them in some detail and then just mention the 2 others. So model 1, we do not know how to perform an integration over this infinite dimensional space of all Riemannian metrics. So I replace all metrics, well, Riemannian metrics, let's say, by metrics obtained by gluings of squares. Gluings of squares. So it seems to be a very crude approximation, but I can just take squares of area epsilon, let's say, of area epsilon. So I just take small squares and I glue them together in large numbers. So in the end I obtain a closed surface composed of 1 billion small squares. And physicists say that this is a good approximation to a Riemannian metric. So if you zoom into your surface, of course you will see that it does not look as a Riemannian metric at all. It is completely, well, it is not smooth, it is flat everywhere except at the vertices of the squares where it has infinite curvature. But then if you do not have a microscope and you look at the surface from far away, you do not see that it is composed of small squares, and it's from far away it looks like just some random metric.
Novikov would say, why don't you use triangles?
Yes, you can also use triangles, but it's for historical reasons actually. Well, I can give you the answer, because this problem is solved using matrix integrals that I have just talked about, because you can see that graphs with vertices of degree 4 is the same as graphs composed of squares. It's a dual picture of the previous problem. And it is technically easier to talk about matrix integrals with x to the power 4, because x to the power 4, if you take the constant lambda of the right sign, is rapidly decreasing at infinity. So there is a range of values of lambda where the integral is well defined. While if you take triangles, you obtain integrals that are never defined, and you have to, well, you have to make some additional effort to define them and to compute them. Okay, so then we obtain the following thing. Okay, let me call QGN the number of quadrangulations, so the number of gluings of n squares that give a surface of genus G. Yeah, I just recalled that I forgot to make one additional remark. That the partition function, well, the partition function is the integral over all possible surfaces not necessarily connected, but as before you can see that f of lambda and kappa, which is the logarithm of z, it's the sum over all genera, well, again, integral over the matrix over a genus G surface, e to the power minus lambda times the area plus mu plus kappa 2 minus 2g. So again, using the same principle, if we take the logarithm, we go from disconnected surfaces to connected surfaces. Okay, so this number QGN, the number of quadrangulations, Q stands for quadrangulations. The number of quadrangulations of a surface is not so easy to determine. And actually it was computed, as I said, using these matrix integrals, which is, you will admit, not a very easy way to proceed. But now there is a result that we will need, that QGN is equivalent as n goes to infinity, so this is what we want. We want to get as many squares as possible, and the genus being fixed. This has the following asymptotics: 12 to the power n times n to the power 5/2 g minus 1 minus 1 times some constant ag.
Да. Разница принципиально между тем, что мы уже посчитали, и вот этим случаем с наличием метрик разных?
Еще раз.
Ну, мы считали вложение графов уже в многообразие.
Да.
А здесь разница в том, что метрики появились разные, да?
Нет, значит... Sorry, first of all, we did not compute anything. We only wrote a matrix integral that expresses this number QGN. So then it is a separate problem how to compute this matrix integral to obtain how to obtain this asymptotic out of this matrix integral. It is still another story.
And one more
Yeah.
question. Does the 12 that showed up there, does have something to do with the zeta minus 1?
Does this have something to do with what?
With the zeta of minus 1. Which is 1 over...
Why zeta of minus? I don't know.
Well, 1 plus 2 plus, etc.
Единица плюс 2 плюс 2.
Yeah, not
1 over 12.
No. This 12 is not at all. You will see that in other models you obtain a different constant in this place. Here you have 12, but you can get anything.
You have 7 more minutes.
7 more minutes, that's good, okay. Okay.
So we give them back to you.
Okay, so now I'll try to compute f. F of lambda and kappa. So this is equal to sum over g and n, qgn, e to the power minus lambda n epsilon. This is the area of the surface, right? It's a surface composed of n squares of area epsilon. Well, plus kappa 2 minus 2g. Now I replace QGN by its asymptotic, so I obtain that this is equal to the sum over g and n of e to the power minus lambda epsilon minus logarithm of 12 to the power, well, times n. Then let me do it like that. E to the power 4/5 of mu to the power 5/2 of g minus 1, because I really want this 5/2 to appear, times n to the power 5/2 g minus 1 minus 1 times the constant ag. Okay, so now I want to, well, this looks as a complicated formula, but actually the important part of it is here. Well, the part to look at. And I'm going to use the following. Okay, so
So I'm sorry, what is mu?
oh, sorry, it's kappa, it's kappa.
Oh, to the right.
Yeah. Excuse me. So there is the following formula: sum of n to the power s minus 1 times e to the power minus delta n is equivalent to gamma of s divided by delta to the power s as delta goes to 0. This is what I'm going to use. So let me first explain where it comes from. This is very easy actually. This is, well, this sum is actually the Riemann sum for the integral t to the power s minus 1 e to the power minus t. Well, I suppose yeah, well, if you make the change of variables, well, if delta is very small, then the step of this sum becomes smaller and smaller. So you can see that this sum approximates this integral, and you obtain this equivalence. And so now I want to use this to compute this sum. So I denote by delta what I have here, lambda epsilon minus logarithm of 12, and I make it tend to 0. And then I denote by y e to the power 4/5 of kappa divided by delta, and this is going to be fixed. So this is a very bizarre trick called renormalization, because instead of two understandable constants lambda and mu, now I obtain just one constant. Well, first of all, so I make everything tend to some limit that is not obvious at all. I should make lambda times epsilon minus logarithm of 12 tend to 0. You could not have predicted that if you don't know that there is this constant 12 in the asymptotic of QGN. Then I introduce this new variable that involves both kappa and lambda in some strange way. But that's actually the only way to make this sum converge to something meaningful. So if I do all that, I obtain that. So now I obtain a function of just one variable y, and it is the following. Gamma of minus.
Okay.
Sorry?
So let's not call it f.
Let's call it small f.
Okay.
A0 y to the power 5/2 plus minus a1 logarithm y and plus sum over g greater than or equal to 2. Again, I don't have enough place. I'll write it again. Okay, f of y equals gamma of minus 5 halves a0 y to the power 5 halves minus b1 logarithm y plus sum over g greater than or equal to 2.
It was A1.
A1, yeah. Gamma of 5 halves g minus 1 ag y to the power 5 halves 1 minus g. And this is the answer to our problem, except that, well, it is well defined up to a change of variables. We can multiply y by a constant, and then we obtain that ag is transformed into c to the power g minus 1 times ag. So this is what we should expect. If we take another model, for example, if we replace squares by triangles, we should obtain in the end the same function, except that maybe instead of y we will get some constant times y. Okay, so now I will mention the other two models, maybe 1 minute per model, just to show you something unusual. So model 2 is using ramified coverings of the sphere, but I will just tell you, so HGN is the number of transitive factorizations of the identity permutation in Sn into transpositions, into 2n plus 2g minus 2 transpositions. So you want to represent the identity permutation as a product of transpositions, and transitive means that using these transpositions you should be able to go from any element to any other element. So you cannot take, for example, all the time the same transposition. Okay, and then you have the following asymptotic: HGN over n factorial to n minus 2g plus 2g minus 2 factorial is equivalent to e to the power n to the power 5 halves g minus 1 times some constant bg. So as you see, you asked me about 12. As you see here, instead of 12 you have e. So this constant can really be anything at all. On the other hand, this power of n is the same, and the constant bg, as expected, are related to ag in the following way. 2 to the power 3 halves g minus 1 times bg.
I understand there is no lecture here after you, so
Yeah.
I will not chase you up.
Yeah. Well, I have. I'm almost finished anyway. I think. Maybe I think I will drop the third model, and I will just write the numbers bg for your amusement, and I will stop at that. So b0 is equal to 1 over square root of 2 pi b1 is equal to 1 over 2 to the power 4 times 3. b2 is equal to 1 over square root of 2 pi 7 over 2 to the power 5 3 to the power 3 times 5. b3, all this is not very characteristic. I will go until the first number that you are sure to recognize. 5 times 7 squared, 2 to the power 16, 3 to the power 5. And finally b4 is the first number that you are certain to recognize. If you find this prime number 2297, then you are sure to recognize the sequence. 5 squared, 11 times 13, and so on. Okay, so I have 3 sequences out of which I showed you only 2, but actually I have one more that all arise in very different problems, and the sequences are actually all very different because they have very different rates of growth. You can understand that from the naive point of view, e to the power n and 12 to the power n are really, one is huge with respect to the other. So if you look at these sequences, both are sequences of integers or rational numbers. If you look at these sequences, you don't see any similarity. But it turns out that if you look at the asymptotic more precisely, first of all you obtain, well, after this leading term you obtain the same power of n, and the constants are the same up to this simple factor. Well, and there is another sequence with the same property, and this is more or less mysterious. So it is motivated by the fact that all 3 are models of the same ill-defined problems, but there is no real explanation why they should coincide. Okay, thank you.